So last class we have studied series LCR circuit, and we have seen how we can select this LCR circuit as a selector circuit for selecting only one frequency. So we know that at resonance there is only the impedance coming from the resistance. So no impedance coming from the inductance or capacitance. So the current, peak current will be E0 by R, which is I0. And now we have to find a quantity which is called quality factor Q. For that we just check the voltage across the inductance at resonance. So at resonance the current maximum is I0, we know that. So the voltage across the inductor or the inductance will be XL into I0, where XL is the impedance offered by the inductor. So the voltage across the impedance is VL, which is equal to XL into I0. XL we know that it is L omega 0 because it is in the resonance condition. We take omega as omega 0. So L omega 0 into the current we know I0, which is E0 by R. So the maximum current I0, which is E0 by R, into we have L omega 0. That means the voltage across the inductor is L omega 0 by R times the maximum voltage E0. So the voltage across the inductor at resonance is L omega 0 by R times the maximum voltage, which is E0. So that means that factor which is used to multiply the maximum voltage, that factor is L omega 0 by R. L omega 0 by R is called the quality factor. So Q, L omega 0 by R is called Q times E0. It is a different kind of factor which is used in this circuit, which we normally used to say the quality factor of LCR circuit. If you are given an LCR circuit, that will be written in that paper or that circuit, underneath it will be written what is the quality factor. So quality factor is just the factor which is multiplied to the maximum voltage to get the voltage across the inductor in that LCR circuit. So that is L omega 0 by R. L omega 0 is the reactance of the coil at resonance. And R is resistance of the circuit. So it is reactance of the coil at resonance divided by resistance of the circuit. And at R is equal to 0, we know that Q will be infinity. And we have shown in the figure where the graph is shown, x-axis we have frequency and y-axis we have current. The current will be infinity when R is equal to 0, and at R is when R is low, Q will be high, and you will have the resonance frequency you will have the maximum current. And at resonance frequency you will have the peak will be at resonance frequency. I didn't denote it there, that that dotted line in the center, that maximum current point is that dotted line represents the resonance frequency. Okay, so we have high quality factor means maximum current. We get maximum current at resonance frequency, or infinite current at resonance frequency if R is 0, if the resistance is 0. So at a particular, so the peak will be narrower when the quality factor is higher. So you can select a particular sharp frequency if the quality factor is higher. So now let us move on to the vector diagram representation of this circuit. So we are here representing the voltage across the resistance, inductance and capacitance as ER, EL and EC. Okay, so ER will be I0 into R, and EL will be L omega into I0, and EC is I0 by C omega. You can see that the voltage across the resistance R is in phase with the applied voltage, and across the voltage across the inductor is 90 degree in advance with the applied voltage, and the voltage across the capacitor will be 90 degree behind. It is lagging behind the applied voltage, and the vector diagram is shown below. You can see there O is the origin and OB. OB represents the voltage across the resistance, which is in phase with the applied voltage. So applied voltage is in the x-axis direction. And the maximum voltage E0 is shown OF. OF is with an angle phi with the OB direction, which is the applied voltage. So the maximum voltage E0 is OF, and the applied the voltage across the resistance is I0R, which is OB, and we have 90 degree in advance. It is leading 90 degree leading the applied voltage, which is the voltage across the inductance, that is L omega I0, which is OC. Okay, OC. And now OD represents the voltage across the capacitor, which is EC, and that is equal to I0 by C omega. Okay, and the resultant voltage, these two voltages EL and EC are opposite direction, isn't it? So if the value of EL is larger than EC, the effective voltage will be along the OE direction. See, OE is the difference in this voltage, L omega I0 minus I0 by C omega, which is the resultant voltage along this OE direction or OC direction. Okay, so I have written that all the values here. If EL is greater than EC, which is the effect, that means the effect, the resultant voltage is OE, which is OC minus OD, which is I into L omega minus 1 by C omega. Okay. And E0 you can find out from the vector diagram. E0 is OB square plus OF square. OB square plus BF square. OF ആണ് E0. So OB is I0R and BF is the same as OE. So OE is L omega into I0 into L omega minus 1 by C omega. So we can take the square and add it and take the square root. So I0 square R square plus I0 square into L omega minus 1 by C omega square whole square root. And then you will get the value of E0. E0 is given I0, you can take it out and take the root. I0 square will be I0 and L omega minus 1 by C omega whole square plus R square whole square root. You will get E0. And E0, if you know, then you can find I0. I0 is E0 by Z. Like Z, we know that it is root of R square plus L omega minus 1 by C omega whole square. We know that. We already studied that. That means we know I0 and we know E0. So I0 and E0, if you know, you can find I and E. E is E0 sin omega t. I is I0 sin omega t minus or plus phi. So tan phi is BF by OB. From that diagram, the vector diagram, phi is opposite side by side. So BF divided by OB. BF is I0 into L omega minus 1 by C omega, and that is divided by I0 into R. That is what written here. I0 get cancelled, so it will be L omega minus 1 by C omega by R. So phi will be tan inverse L omega minus 1 by C omega by R. This is the value which we got earlier when we derived it. So this is the vector notation only. From that we can derive the same values of phi and I. and E0. Sorry, E and E0. Okay, that's all for this LCR series circuit. Now we are going to check a problem. See here, problem is written. A circuit consists of a non-inductive resistance of 50 ohms and inductance of 0.3 Henry and resistance of 2 ohms and a capacitor of 40 microfarad in series and is supplied with a 200 voltage at 50 Hz. Find the impedance of the circuit, the current and the lag or lead and the power in the circuit. So here we have the LCR series circuit. It is said that it is series LCR. So we first find all the values L, C and R. Total R will be, it is written here 50 ohms resistance you have, and there is 2 ohm resistance for the inductor. So inductance is there for the coil, inductance is there, and for coil resistance also will be there. So the total resistance will be the resistance of the resistor and the inductor, which is 50 plus 2. So 50 plus 2, 52 ohms will be the total resistance. And the frequency is given omega, which is 50 Hertz. So if you have to write angular frequency, it should be 2 pi nu. So 2 pi into 50, which is 100 pi. Okay. Now the total impedance you have to find. The total impedance, we know that it is square root of R square plus L omega minus 1 by C omega whole square. Isn't it? So R we know 52 and L omega, L we know 0.3 into 100 pi minus 1 by 40 into, it is microfarad, so it should be 10 raised to minus 6. Micro always is 10 raised to minus 6. So 40 into 10 raised to minus 6 farad into 100 pi and whole square. So if you calculate that, it will be 53.97 ohm. That is the effective impedance of the circuit. So we have found out the first question. Find the impedance. So the first question we have found the answer. Now we have to find the current, isn't it? Current we know, if you know the impedance, you can find the current. IRMS is ERMS by Z. Z is the effective impedance. We are supplied with a voltage 200 volt, that is the root mean square voltage, and 200 by 53.97 you will get the IRMS 3.71 ampere. That is the root mean square current. And if you want to find the maximum current, you need to multiply it with a root 2. Root 2 IRMS you will get maximum current. Okay, so root 2 into 3.71 ampere. Now lag or lead, it is asking lag or lead and the power of the circuit. So if you have to find the lag or lead, you need to find L omega minus 1 by C omega. So if it is positive, so let us find that. L omega is 100 pi into 0.3, which is 94.2, and XC, which is 1 by C omega, and that is 1 by 40 into 10 raised to minus 6 into 100 pi, which is 79.6. So see that XL is greater than XC. So what does it mean? XL greater than XC means the current across is lagging behind the applied EMF. So the current is lagging behind the applied EMF. And the lag is angle phi, which is tan inverse L omega minus 1 by C omega by R. Okay. So tan inverse 94.2 minus 79.6 divided by 52, which is 15 degree 39 minute, which is the angle of lag. And the power is ERMS into IRMS. You can get 742 ampere voltage or watt. We can say that watt. And that is the apparent power, but we need to find the true power. In order to find the true power, you need to find the power factor. Power factor we didn't study, but you should remember that power factor is cos phi. If the lag we know phi and the angle we know, then you can find the power factor, and that is cos phi from that diagram, from that vector diagram. What is the cos phi angle? Cos phi means I0R by what? It is cos phi is I0R by the square root of R square plus L omega minus 1 by C omega whole square. The hypotenuse is I0 R square plus L omega minus 1 by C omega into I0 whole square. So that is hypotenuse. So that I0 will get cancelled there. I0R divided by I0 into nalle. Appa I0 mellam thaleyum kattaipo. So I0 cancel I. So it is R by root of R square plus L omega minus 1 by C omega whole square. That is called power factor. Cos phi. Cos phi is power factor. And we can find that it is 0.964. So you need to multiply this power factor to the apparent power, and then you will get the true power. So 0.964 into 742 watt, which you get is 716 watt is the answer. Okay. So next class we will study the J operator method.